Okay. Whole, 0 over 0, got it. Part B, discontinuity. What's going on? It's a piecewise. Why does it have to be a piecewise? Yeah, 2 different pieces. They don't even match up. What kind of normal function is that? What's a normal function? Perpendicular. Anyway, come back. Just kidding. Piecewise. It's a piecewise discontinuity, but how could I explain it?
One-sided limit.
What am I going to say?
Do not agree.
Whenever the one-sided limits towards the C don't agree, isn't there going to be a jump or a break discontinuity? So it's a jump or break discontinuity. You guys nailed it. It is a piecewise function that doesn't match up, whose pieces don't meet at the separator. At the separator. Bringing in all these big ideas. Part C. What kind of discontinuity? Vertical asymptote, right? So we could say that it has an infinite limit. We could say it's a vertical asymptote. When we plug in, remember, that's infinite form, so number over 0, right? Can't factor out, can't be removed. Does anybody notice, though, what's weird about part C?
There's a dot.
There's a dot, which means what kind of function must this be? Piecewise. Because there's a function who normally has a vertical asymptote at x equals c, but they also randomly are like, but I'm going to assign at some point k a point at that c, or for that x value c. So this actually is going to be a piecewise as well. Doesn't mean all vertical asymptotes are, or all functions with vertical asymptotes are, but this one is because of that funky point right there. How about the last one? He's piecewise too, because there's like a normal function with the whole, just minding his own business, and the piecewise function is like, haha, and it's like, you fail. Now, one of the directions you're going to be given either on APs for AP questions or in your homework is going to be, how can I make a piecewise to fill in that hole? That's going to be one of your directives. However, right now we're just looking at graphically how do these all work out and what's going on. But when you guys see a piecewise function, and when it says, hey, it's this function for all x not equal to c, and it's this random whatever for x equals c, this is what they're trying to do. They're trying to fix the discontinuity. And they might fix it incorrectly, which means it's still discontinuous. They could try to fix it, but it can never be fixed. It's going to infinity. Or they could fix it correctly and fill in that hole, which basically is the same as factoring it out. All right, now, moving on. While I pass out papers, I want you guys to write the definition, not like, you can draw it without picking up your pencil. That was Algebra 1. Definition of a continuous function. Well, description is you can draw it without picking up your pencil, but the definition is 3 conditions have to be satisfied. But the nice thing is all 3 are basically summarized in the third. If the third is true, all 3 of them will be true. So if you were to only memorize 1, the third is the most important. However, I'm saying the whole shabam is important. Why am I making this?
Oh no.
Oh, I'm serious. It gets way worse. Write down definition of continuity, not way worse. While you guys are writing and doing notes, I'm going to be passing back stuff. Okay? The rows might be a little bit off. Remember, you should be writing row number as a heading as well. If there's anybody not in your row and you know who they are, get them their papers. There are Chapter 1 homework packets in here. There are forever quizzes in here. As of Monday afternoon, all of these were updated on Redwood. You will also be getting back your AP number 2s, which are graded, but not for a grade yet. I was keeping you accountable, so if you didn't have it ready for me, I am going to take off some partial credit. If you don't turn it in at all with the limits, which, well, the opportunity just passed, definitely have off partial credit. So I'm giving you some accountability, but I do want you to be able to try the ones you got wrong again. One quick note, kiddos. If I ever give you a strictly multiple choice assignment and I don't see any work, do I assume that you did that well and did it correctly and did it on your own?
Or integrity.
No, either I assume that you stole answers from others, or I assume that you didn't really try it. So if I give you a strictly multiple choice assignment and there is no work shown. Now some of you guys were sparse on work and I wrote you warnings for next time that there better be work shown when you turn this thing in at the end of the chapter. Some of you guys got warnings, but at least you showed me some. Some of you guys showed no work and then I say, sorry, it's just as good as not doing it. What's the point if there are just circles with no work shown? So if you guys have questions on that, you can come and I can quiz you on harder ones and see if you're able to do them in your head just as well as you did the ones on your paper. But for the most part, I can tell which problems deserve work and which ones don't, especially for my kiddos who did put a lot of work into AP number 2. They know that there should have been work shown. So if you did not have any work shown, I assume you did not do it right. You did not do it, you did not try it, or you just stole answers from someone else, or maybe both. If you have any questions, you can ask me about any of the grades on homework packets or on quizzes or on AP number 2s. My guys who didn't show work on AP number 2, make sure you show it to me by the time you turn it in. I know it seems silly, but it's not. Alright guys, I'm going to fill in just a couple clues because right now it's all like math lingo, which some of you guys are like, got it, good, let's go on. Others of you are like, no clue. So, F of C defined. Can anyone, you have 4 graphs above this definition. There are 4 different graphs. Question, where is a graph, or which function fails condition 1? What does it mean for F of C to be defined? What do you guys think? What's one that fails? I heard B first. Does B actually fail? Is there a Y that goes with, there's a point for when X equals C for B. A. Is there a point for when X equals C? No. So A does fail 1. Does B have, or C have a point? Yep. It's a horrible point, but that does. Does D? Yep. It's a bad point, but it does. So therefore, B and C and D all have points that are defined. So let me go ahead and change this. Not change it, but add to it a little bit. You could put this in your forever as well, or you could just write it as little hints to remember. When I say F of C is defined, I mean at X equals C, a point exists. A point exists. I'm not asking as to whether it's jumping or breaking or like randomly in a vertical asymptote. I'm just saying, is there a point? If I plug in C, can I get out a Y? Is there, if I plug in an X, can I get out a Y at C? Is there a point? Which one or ones fails condition 2? The limit as X approaches C, both sides, of a function exists. The third one, why? It exists, but does it actually exist? What's it equal? Infinity. Well, if I have a limit as I come towards a constant equaling infinity, what is there defined to be? A vertical asymptote, which is a discontinuity. So you could think about part C, you could think about it as failing condition 2. Technically it does because its limit doesn't exist as a constant. But what's the one I probably meant more specifically? B. Why doesn't the limit exist?
Different values.
They don't agree. As I come from both sides, the one-sided limits don't agree, therefore the limit does not exist. So when I'm talking about down here in my definition, the limit existing, I mean the one-sided limits exist and agree, right? Just by definition of what we talked about before, or pulling on what we've learned before. And then condition 3, why am I saying that's the most important? Well, for condition 3 to work, don't you have to have a point? And don't you have to have a limit? And don't they have to be the same? So for condition 3 to work, I'm going to have a point because that has to be a value. I'm going to have a limit because it's going to equal a number. Those two have to match. So guys, which one fails condition 3? You could say C because my limit is positive infinity and my point is nowhere near like matching, right? And more specifically, I probably mean B. The limit doesn't exist in B, so I can't even start. But D, does the limit exist? Maybe I should zoom in on this for just a second. There's way too many dots. We'll just pretend. For part D, does the limit exist? Yeah, it's right about there, right? Does the point exist? Yep, his y value is right about there. But are these the same? No. Doesn't agree. The limit doesn't agree with the point, so therefore it has to be discontinuous. Now, guys, when I showed you these at the beginning of class, most of you were like, well, duh, those aren't continuous. You have to pick up your pencil when you're drawing the graph. Like, well, I guess you could cheat and like go around a few times, so that's cheating. If I'm just trying to cover the graph, I cannot go over that whole. Here I obviously have to pick up to move. Here I have to obviously pick up to finish my graph. Here, once again, I have to pick up to finish. So if you go back to that basic algebra 1, pick up your pencil 2, that's true, but this is the actual mathematical proof as to why they're discontinuous. If any function fails any of these, the main climax is the third one. If a function passes the third one, it's going to pass the others. It's going to be continuous. But if it fails any of them, it's discontinuous at x equals c. Quick recap then of all of our discontinuities. We've talked about them a lot. The nice thing is with solving for limits, we had to deal with holes and vertical asymptotes and all that jazz. But just so we have in the section on continuity a quick reminder. And we're going to expand just a little bit. Two types. We have our removable. Those are our holes, right? We have our 0 over 0, which indicates to us that there are common factors, aka if I could only simplify, if I could only factor and reduce, then I'd be fine. I would get rid of my hole, hence why it's called removable. And you guys saw lots of examples on the page before, so I'll just go ahead and just do a silly example. Non-removable. We know that vertical asymptotes are non-removable. However, we have a couple more categories. There are also technically breaks and jumps, which both have to do with piecewise, which we saw on the page before. Vertical asymptotes for like a normal rational function with a polynomial on top and a polynomial on bottom. Yeah, okay, if I have a number over 0, it's going to be a vertical asymptote. It's not going to factor out, so it's non-removable. But I can also have piecewise functions that don't match up, and that's trickier to see, trickier to realize. So I could have anything from, they like just leave a gap out of the domain, which is really rare because this one's really easy to see because you just have whole sections of x's missing. The one they like to use a whole lot more is where they match it up at a set value, at a separator. They have it, from x less than or equal, less than, and then x greater than or equal to, so you think it's continuous, but they don't even match up. And then the obvious vertical asymptotes that we've already been dealing with our limits, like 1 over x or other functions similar. I told you there were a lot of ideas today. Technically, all of this that we've been talking about is a function continuous at one point. However, as we know, whenever we're talking about domains, is it easier to talk about all the different places where it works or the few places it doesn't, if any? Yeah. So continuity is the same dealio. Instead of talking about all the different places it works and testing, like, does it work here? Yes. Does it work here? Yes. Does it work here? Yes. We're going to think about them as working on full intervals. So we're not going to test them at individual points unless we're trying to find a point where it doesn't work. So we can talk about a function being continuous on an open interval. It could be between two endpoints, but not including, and the definition of continuity of a function still is upheld, still works. We could even talk about infinite open intervals, a to infinity or negative infinity to b, or even all real numbers. And the definition of continuous still works. Only a few of you would really actually question as to how it works. Because if it's held off by A and B, some of you might be like, wait a minute, but the definition says you have to approach from both sides. But if it's open, I'm not actually stopping at A. Any point I choose, I can choose a point to the left of. That's just a little bit smaller in increments, and then I can go ahead and approach. It's legal. The problem is when I start talking about continuity on closed intervals, because once I close it, it's like, how do I get to the left of that endpoint? And that's a little tricky, but the nice thing is we're not going to really have to stress about it too much, because there's actually just a new way of defining continuity for closed intervals. So it's not super crazy. I kind of skipped a few things, but that's okay. I want to get these big ideas down today, so we can just work on problems tomorrow. We'll go back to that, but it can be after in your notes. It's okay. For a closed interval, you're like, or I would say, you can't come from the other side of A, which is why we define just the limit approaching A from above and just the limit approaching B from below. So technically, that's a typo. The definition gets changed just a little bit, but the nice thing for you guys is, isn't a forever card. The nice thing for you guys, you're not going to have to state what you're doing if it asks you whether or not it's continuous at like an endpoint. You can just think, okay, the limit as I come from above, does it match the actual value at the endpoint itself? So if they're asking about if it's continuous at an endpoint, you can just approach from above or from below, depending on which end it is. Oh, B negative, because you can, if it's a closed, I can't come from above because I'm only looking inside my interval, so I have to come only from below. So it just changes the definition a little bit, but it's not in a huge way that's going to affect you. You might just see it in a few word problems. Now, speaking of continuity, that closed is just going to be down there at the bottom. There are a few functions that are continuous at every point within their domain. We talked about domain problems when we were talking about pre-cal review. So we know, even-powered radicals, the argument can't be negative. Denominators can't be 0. Logarithmic arguments have to be greater than 0. But here are a few common functions that you never have to worry about as long as you're dealing with values inside the natural or the implicit domain. Polynomial, radical, trigonometric. Now you might say, trigonometric, there's so many vertical asymptotes. I know, but the domain says not equal to those asymptotes. So it's within their domain. And logarithmic exponential. We almost made it up to period 1. If they ever ask you about one of these types of functions, about the continuity, you can just say, oh, of course that's continuous as long as it's in its domain. You don't even have to test the different conditions. Homework, as I said, homework number 8 isn't due until Friday, but if you can start tonight, it will make your life a lot easier. But some of you just need to catch up in other classes so you can spend time on mine tomorrow night. You can look at your AP number 2s, etc. I'll be here after school if you have any questions for me. Did you understand number 2 why I said doesn't count? So next time, just show me. I'm coming. Someone had a question.
You know what?
You guys will, did you?
You can
Stop the recording. Okay. Bye guys. Happy lunchtime.